From chapter 6 on, we present the applications of the thermodynamics theory we have learned up to now. Generally, we won't display new formulas unless strictly needed by the examples or if we introduce new concepts meanwhile. We remember that the formulas are assumed at the very end of each chapter. In this lecture, we show an application of the lesson 5, where we introduced the mixtures air and vapor. We will see how it is possible to generate vacuum in a system by a solely thermodynamic process, and we compare it with a conventional system, also mechanically driven, using vacuum pumps, to assess if and when it is beneficial. Let's see together what is a problem. A recipient having a volume capital V is initially full with steam and nitrogen under following conditions: pressure 1200 kPa, temperature 185 degrees, volume 3.2 cubic meter, and the mass of the liquid is 40 kg. Then the recipient is put into communication with the ambient at atmospheric pressure, that is the condition B, where the pressure is 100 kPa and the volume stays the same. Soon after the atmospheric pressure is achieved, in the recipient is applied the vacuum, and this is the condition C. The pressure is 50 kPa and the condensate is taken out by a cyclone. Then the remaining gaseous mixture, steam plus nitrogen, is sent to a condenser cooled by water. And this is the condition D, where the pressure is still 50 kPa and the temperature 50 degrees. We need to find the total condensate taken out from the process and the heat demand, in this case is a cooling demand, required by the condenser. How the cooling in the condenser is achieved? The tank is sprayed by water. The water is circulated by a pump and cooled by an external heat exchanger. The level controls open a blow-down valve to empty the accumulated condensate. The remaining steam and nitrogen that is incondensable are eliminated via an independent vacuum pump or jet pump. The vacuum level and the temperature in the tank can be freely chosen in a certain range. The vacuum is actually achieved for condensation of the steam. It is a pure thermodynamic process. Let's define our model. The fluid 1 is steam as real gas, the fluid 2 is nitrogen as ideal gas, and the parameters for the nitrogen are given. R2 is known, Cp2 is also known, Cv2 is Cp2 minus R2, and the reference data for the nitrogen are temperature 25 degrees, pressure 100 kPa, entropy 0 kJ per kilogram per Kelvin, and enthalpy 0 kJ per kilogram. The state A can be calculated because we have 4 variables known, as displayed in the slide number 3. For the steam, we get by the temperature the specific volume of the vapor, the specific volume of the liquid, and then the volume of the liquid as the product of the specific volume and the mass. Moreover, we can get the volume of the vapor as difference between the total volume and the volume of the liquid already calculated. The mass of the vapor is the ratio between the volume of the vapor and its specific volume, and the steam quality is the ratio between the mass of the vapor and the total mass of the steam. We get 31%. For the nitrogen, from the temperature, we calculate the partial pressure of the steam P1, then the pressure of the nitrogen is the difference between the total pressure and the pressure of the steam. The specific volume we calculate by means of the state equation, and the mass as a ratio between the volume, which is common among steam and nitrogen, and the specific volume already calculated. Let's calculate the remaining thermodynamic variables of the state A. For the steam, we calculate the specific enthalpy by means of this formula, where all the variables are known. In particular, is known the steam quality X, and the specific enthalpy of the vapor as well as the specific enthalpy of the liquid are only function of the temperature. Similar formula for the specific entropy of the steam, and for the nitrogen, the specific enthalpy we can calculate because it is only function of the temperature, as well as we can calculate the specific entropy being a function of temperature and partial pressure of the nitrogen. For the mixture, the mass is the sum of the mass of the steam and the mass of the nitrogen. The enthalpy is the sum product between the masses and the specific enthalpies already calculated, and the specific enthalpy of the mixture is, per definition, the ratio between the total enthalpy and the mass of the mixture. Similar formulas we can use to calculate the total entropy and the specific entropy of the mixture. All the results are assumed in the table aside. Let's find now the state B. The transformation AB is isenthalpic. The mass in the recipient changes because of the discharge. We calculate first the state B star, considering the complete mass and assuming a temperature of the mixture of 95 degrees, to be verified later. From the temperature we calculate the steam properties, the pressure, the specific volume of the vapor, the specific volume of the liquid. And for the nitrogen, the pressure is the difference between the total pressure and the pressure of the steam, and the specific volume we calculate from the state equation. The total volume is the product of the mass of the nitrogen and its specific volume, remembering that the mass won't change, and since the total volume is the same for the nitrogen and for the steam, we can calculate the volume of the steam by this formula, and from the volume of the steam quality X, by using this expression. With the steam quality X, it is possible to calculate the vapor mass, the enthalpy and the entropy of the steam. The mass of the vapor is then 6.45 kg, the mass of the liquid 51.70 kg, the enthalpy and the entropy we calculate with the formulas we have already seen. For the nitrogen, we calculate the enthalpy, that is a function of the temperature only, and the entropy, that is a function of temperature and pressure. For the mix, we calculate the total enthalpy as sum product of the masses and the specific enthalpies. In the same way, we calculate the total entropy. And since the total enthalpy has to stay constant, to be the same as per slide 6, we need to change our assumption for the temperature till when this condition is achieved. Finally, we find for the temperature the value 98.36 degrees. And then we can recalculate all the parameters. In particular, the volume is 45.4 cubic meter. What is the mass left in the recipient? The density of the mixture is kept constant. Therefore, the mass is the product of the mass of the state A into the ratio of the volumes. We find 4.22 kg. that represents 7% of the total mass. As a consequence, also the steam and the nitrogen masses will be reduced accordingly. We find for M1 4.097 kg and for M2 0.127 kg. Let's find now the state C. We proceed in the same way as for the state B, and also in this case we look for the state C star while considering the total mass inside the bladder being expanded up to the pressure 50 kPa. The result says that V of the state C star is 6.44 cubic meter, but since the recipient volume is only 3.2 cubic meter, then the volume to be exhausted is the difference, 3.24 cubic meter, and consequently the mass of the state C, that is the mass inside of the cyclone, is the product of the mass of the state B and the ratio of the volumes, 2.125 kg, and the found temperature is 80.27 degrees. We find the temperature with the same procedure used for the state B while keeping the same enthalpy, because the transformation is isenthalpic, as we can see from the chart on the right side. The mixture in the cyclone represents the state C. From the mixture, the condensate will be taken out, and then the steam quality changes to 100%. This is the state C prime. Specific volume, enthalpy, entropy of the steam and of the mixture will change, as well the total mass. We can see all the changes in the right table in the last column. The changes are also evidenced in yellow with respect to the state C. The last transformation C'D is isobaric, the mixture will be cooled and the mass is kept constant. How to find the state D? What is known is the pressure 50 kPa, the temperature 50 degrees, and the mass of the steam and the mass of the nitrogen. We assume a value for the steam quality. Let's say X equals 5%. From the temperature, we calculate the steam properties: pressure of the steam, specific volume of the liquid, and specific volume of the vapor. Then with this formula, we calculate the specific volume of the steam and the total volume as a product of the mass of the steam and its specific volume. We find 0.58 cubic meter. For the nitrogen, we know the pressure is the difference between the total pressure and the pressure of the steam. Specific volume we calculate from the state equation, and the total volume is the product of the mass of the nitrogen and its specific volume. We find 0.16 cubic meter. That is unfortunately not matching with the capital V1, that is the total volume of the steam. Then we need to change X till when the two volumes are the same. We find X equals 9.4%. All the corresponding parameters are now updated in the table on the right side, on the very last column. How to achieve the cooling? The cooling demand is QC'D, that is the product of the total mass and the difference of the enthalpy of the two states, that is negative 2308.6 kJ. Let's assume we have a disposal water at 40 degrees. By mixing with the steam, the water temperature raises to 50 degrees, so delta T is 10 degrees. The water cooling amount will be capital M negative QC'D over delta T into CV, where CV is the specific heat of the water, 55 kg. Assuming the process time is 1 minute, then the mass flow is 3.3 cubic meter per hour. The corresponding pump power for a delta pressure of 20 meters is 360 watt. The capacity of the heat exchanger is the ratio between the heat and the delta T, also 38.5 kilowatt. The condensate amount of 0.95 kg per minute, as displayed in the slide 11, will be drained by the same pump via an automatic valve, level controlled. The remaining steam and nitrogen has to be exhausted by a vacuum pump or a jet pump. The lesson will continue in the next presentation, where we will see if the vacuum generated by the steam is more or less convenient than the vacuum generated by a conventional pump. Thanks for your attendance. See you again. Bye bye.